The cold front arrived over Houston at 03:47 on a Wednesday in mid-January, dropping ambient temperatures from 52 degrees Fahrenheit to 28 degrees Fahrenheit within 4 hours. By 0800, outdoor temperatures had stabilized at 26 degrees Fahrenheit with sustained winds from the north at 18 miles per hour, producing a wind chill of 14 degrees Fahrenheit. The National Weather Service had issued a hard freeze warning 36 hours prior, advising that temperatures would remain below freezing for approximately 40 consecutive hours, the longest such period projected for the Houston metro area in 8 years. Residential heating systems across the city activated in response to thermostat calls beginning around 0400, with natural gas demand from the residential sector increasing from baseline overnight consumption of approximately 1.2 billion cubic feet per day to 2.8 billion cubic feet per day by 0900. Electric heating load, representing roughly 35% of Houston area homes relying on heat pumps or electric resistance heating, rose from 2,100 megawatts to 4,800 megawatts during the same period. CenterPoint Energy reported normal gas pressure across distribution networks, with pipeline delivery matching demand within operational parameters. ERCOT reported grid stability with reserve margins at 18%, well above the 13.75% threshold considered adequate for reliable operation. No system alerts were issued. All infrastructure indicators suggested normal cold weather response. Furnaces cycled on. Thermostats registered indoor temperatures and called for heat. Compressors activated. Ignition sequences completed. Yet, across a statistically significant portion of residential structures, indoor temperatures began a gradual decline that would continue throughout the day despite continuous system operation. Houston residential heating infrastructure was designed primarily for brief cold episodes rather than sustained freezing conditions. The majority of single-family homes constructed after 1990 utilized natural gas forced air furnaces rated between 60,000 and 100,000 BTU per hour, sized according to Manual J load calculations that assumed outdoor design temperatures of 32 degrees Fahrenheit and indoor set points of 70 degrees Fahrenheit. Heat pump installations, prevalent in homes built after 2010, were typically sized for cooling loads with heating capacity as a secondary consideration, reflecting Houston's climate classification as humid subtropical with only occasional freezing events. Building envelope characteristics reflected similar assumptions. Attic insulation levels averaged R19 to R30, below the R38 to R49 recommended for colder climates. Wall insulation and wood frame construction typically consisted of R13 fiberglass batts. Window assemblies were predominantly single-pane or dual-pane, with U factors ranging from 0.40 to 0.65, optimized for solar heat gain reduction rather than thermal retention. Air infiltration rates, measured in air changes per hour at 50 pascals pressure differential, averaged 7 to 12 ACH50 in structures built before enhanced energy codes, indicating significant envelope leakage. These design parameters functioned adequately during typical Houston winter conditions, where cold periods lasted 6 to 18 hours and outdoor temperatures rarely remained below 28 degrees Fahrenheit for extended durations. Equipment cycling patterns under normal conditions involved 15 to 25-minute run periods followed by 20 to 40-minute off periods, allowing indoor temperatures to stabilize between cycles and preventing equipment from operating continuously at maximum output. On this particular Wednesday, however, ambient conditions departed from the statistical envelope upon which residential heating systems had been designed and installed. Between 0800 and 1200, outdoor temperatures held steady at 24 to 26 degrees Fahrenheit, with wind speeds maintaining 15 to 20 miles per hour. Indoor temperature data from residential smart thermostats aggregated across approximately 47,000 Houston area homes by Ecobee and Google Nest systems showed an initial response consistent with normal heating operation. Average indoor temperatures at 0800 registered 68.2 degrees Fahrenheit, slightly below typical overnight set points due to the rapid temperature drop during early morning hours. By 900, average indoor temperatures had risen to 68.9 degrees Fahrenheit as heating systems responded to thermostat calls. However, between 900 and 1200, despite continuous furnace operation in most structures, average indoor temperatures increased only to 69.1 degrees Fahrenheit, then began a steady decline. By 1200, aggregated indoor temperature data showed an average of 68.3 degrees Fahrenheit, representing a net loss of 0.6 degrees Fahrenheit over 3 hours of active heating. The distribution pattern revealed significant variation. Approximately 32% of monitored homes maintained indoor temperatures at or above 69 degrees Fahrenheit. Approximately 41% registered temperatures between 66 and 69 degrees Fahrenheit. Approximately 19% showed temperatures between 63 and 66 degrees Fahrenheit. Approximately 8% had fallen below 63 degrees Fahrenheit. These patterns correlated with building age, construction type, and heating system configuration. Homes built before 1985 with original HVAC equipment showed the steepest temperature declines. Structures with heat pump systems lacking auxiliary electric resistance strips demonstrated reduced heating output as outdoor temperatures fell below the effective operating range for refrigerant-based heat transfer. Single-story homes with large window areas and minimal attic insulation exhibited faster heat loss rates than two-story structures with smaller window-to-wall ratios. The thermal gradient between indoor and outdoor environments had created a heat loss rate that exceeded the sustained output capacity of installed heating equipment operating within design parameters. Natural gas furnaces in residential installations typically achieve rated output capacity only during the active portion of their duty cycle. A furnace rated at 80,000 BTU per hour does not deliver 80,000 BTU during an hour of operation. Rather, it delivers that output rate while the burner is firing, with actual hourly heat delivery depending on the percentage of time the unit operates. Under normal conditions, furnaces cycle on and off to maintain temperature, running perhaps 30 to 40 minutes out of every hour during cold weather. On this Wednesday, thermostat calls for heat became continuous. Furnaces that would typically cycle began running without interruption, maintaining burner operation for periods exceeding 2 hours. This operational pattern pushed equipment into thermal regimes not typically encountered in Houston installations. Heat exchanger surface temperatures rose to sustained levels near the upper design threshold. Blower motors operated without the cooling intervals normally provided by off-cycles. Flue gas temperatures remained elevated continuously rather than cycling between active and standby states. While none of these conditions exceeded equipment safety limits or triggered automatic shutdowns, they represented operational stress profiles outside the typical duty pattern for which the equipment had been sized and installed. Moreover, continuous operation revealed a second constraint. Even at maximum rated output, many systems could not offset the rate of heat loss occurring through building envelopes under sustained 26-degree Fahrenheit outdoor temperatures with 18-mile-per-hour wind. A home losing 75,000 BTU per hour to the outdoor environment cannot maintain temperature with a furnace delivering 70,000 BTU per hour, regardless of how long that furnace operates. The thermal deficit accumulates as a slow, steady decline in indoor temperature. Heat pump systems encountered more immediate limitations. Air source heat pumps operate by extracting thermal energy from outdoor air and transferring it indoors through refrigerant compression cycles. This process becomes progressively less efficient as outdoor temperatures decline. Coefficient of performance, the ratio of heat delivered to electrical energy consumed, typically falls from 3.0 at 47 degrees Fahrenheit outdoor temperature to 1.8 at 17 degrees Fahrenheit outdoor temperature for standard residential heat pump units installed in Houston. At outdoor temperatures of 24 degrees Fahrenheit to 26 degrees Fahrenheit, heat pumps in the study area operated with COP values between 1.9 and 2.1, delivering approximately 60 to 70% of their rated heating capacity at the 47 degrees Fahrenheit rating condition. For a heat pump rated at 36,000 BTU per hour at standard conditions, actual output at 25 degrees Fahrenheit outdoor temperature ranged from 21,600 to 25,200 BTU per hour. Many installations included auxiliary electric resistance heating strips designed to supplement heat pump output during extreme cold. However, approximately 40% of Houston area heat pump installations consisted of base models without auxiliary heat, relying solely on refrigerant cycle operation. These systems encountered a fundamental thermodynamic constraint. Below certain outdoor temperatures, heat pump output capacity falls below the building's heat loss rate even during continuous operation. Indoor temperatures in homes with heat pumps lacking auxiliary strips began declining earlier and more rapidly than in homes with gas furnaces or heat pumps with electric backup. By 10 o'clock, structures with base model heat pumps averaged 67.1 degrees Fahrenheit indoors. By 12 o'clock, this average had fallen to 65.3 degrees Fahrenheit. By 1400, it reached 63.8 degrees Fahrenheit. The systems remained operational, compressors running, refrigerant circulating, but thermal output insufficient to match envelope losses. Thermostats continued to call for heat, equipment continued to respond, indoor temperatures continued to fall. Building envelope performance became the dominant variable determining indoor temperature retention. Thermal conductivity through walls, ceilings, windows, and infiltration pathways created heat loss rates that varied by structure but followed predictable patterns based on construction characteristics. A typical 2,000-square-foot single-story Houston home with R19 attic insulation, R13 wall insulation, dual-pane windows with U-factor 0.50, and air infiltration at 9 ACH50 would experience heat loss of approximately 68,000 BTU per hour at a 44 degree Fahrenheit temperature differential between indoor, 70 degrees Fahrenheit, and outdoor, 26 degrees Fahrenheit, environments under calm conditions. With 18-mile-per-hour wind, infiltration-driven heat loss increases by approximately 15 to 22%, raising total heat loss to between 78,000 and 83,000 BTU per hour. A furnace rated at 80,000 BTU per hour operating continuously would deliver approximately 72,000 to 76,000 BTU per hour, accounting for distribution losses through ductwork in unconditioned attic spaces. The resulting thermal deficit of 2,000 to 11,000 BTU per hour would produce an indoor temperature decline of approximately 0.8 degrees Fahrenheit to 1.2 degrees Fahrenheit per hour in a structure with typical thermal mass. Over a 12-hour period of sustained cold, this translates to a temperature drop of 10 to 14 degrees Fahrenheit, even with heating equipment operating at full capacity. Homes with poorer envelope characteristics, single-pane windows, R11 wall insulation, higher infiltration rates, experienced proportionally greater heat loss. Conversely, well-insulated structures with R38 attic insulation, low infiltration construction, and high-performance windows maintained indoor temperatures more effectively, though even these buildings showed gradual temperature decline under prolonged exposure. The physical reality was straightforward. Thermal energy was leaving these structures faster than installed heating systems could replace it, and the duration of cold exposure allowed no recovery period during which systems could restore lost thermal capacity. Utility scale data confirmed system-wide patterns. CenterPoint Energy recorded natural gas consumption in the Houston metro area reaching 3.1 billion cubic feet on Wednesday, representing 258% of typical January daily consumption and the third highest single-day residential demand on record. Gas distribution pressure remained within normal operating ranges throughout the event, with no curtailments or service interruptions reported. Electric load data from ERCOT showed Houston area demand reaching 6,200 megawatts during afternoon peak hours, with residential heating contributing an estimated 5,100 megawatts, or 82% of total load. Grid frequency remained stable at 60.0 Hz with minimal deviation. No generation units tripped offline. Reserve margins remained above 15% throughout the day. From an infrastructure delivery perspective, the event represented successful operation under high-demand conditions. Energy reached end users continuously and reliably. Yet smart thermostat data aggregated from connected devices revealed that energy delivery did not translate to temperature maintenance. At 1400, average indoor temperature across monitored Houston homes had declined to 67.4 degrees Fahrenheit. At 1600, it reached 66.8 degrees Fahrenheit. At 1800, it fell to 66.1 degrees Fahrenheit. Temperature distribution had shifted substantially from morning baselines. Homes maintaining 70 degrees Fahrenheit or above decreased from 32% at 0900 to 18% at 1800. Homes between 66 degrees Fahrenheit and 70 degrees Fahrenheit increased from 19% to 24%. Homes below 63 degrees Fahrenheit increased from 8% to 10%. The correlation between energy consumption and thermal comfort had broken down. Systems consumed record quantities of fuel and electricity while failing to maintain design indoor conditions across a significant portion of the building stock. Operational patterns revealed equipment functioning at the limits of thermal capacity rather than experiencing mechanical failure. Furnace runtime data from connected HVAC control systems showed average daily runtime increasing from typical January values of 4 to 6 hours per day to 18 to 22 hours on Wednesday. Heat pump runtime data showed similar patterns, with compressor operation exceeding 20 hours in many installations. These extended run periods occurred without triggering safety shutoffs or fault conditions. Flame sensors confirmed burner operation. Limit switches registered acceptable heat exchanger temperatures. Pressure switches verified adequate combustion airflow. Ignition systems functioned normally. Blower motors maintained design CFM output. Refrigerant pressures in heat pump systems remained within operational ranges. Equipment diagnostics showed systems operating according to designed responses. Thermostat calls for heat were received, heating cycles initiated, burners fired or compressors engaged, and conditioned air circulated through occupied spaces. The failure was not mechanical, but thermodynamic. Designed heating capacity, adequate for typical Houston winter conditions involving brief cold periods with rapid recovery, proved insufficient when cold conditions persisted beyond the duration envelope used in equipment sizing calculations. Manual J load calculations, the industry standard methodology for residential HVAC sizing, typically assume outdoor design temperatures based on 99% winter design conditions, the temperature that is exceeded 99% of hours during December, January, and February. For Houston, this value is 32 degrees Fahrenheit. Equipment size to maintain 70 degrees Fahrenheit indoor temperature at 32 degrees Fahrenheit outdoor temperature lacks capacity reserve when outdoor temperatures fall to 26 degrees Fahrenheit and remain there for 40 consecutive hours. The system performed as designed within its design envelope. The ambient conditions exceeded that envelope. Temperature recovery patterns demonstrated the second-order effects of thermal capacity constraints. As outdoor temperatures began rising after 1900, increasing from 26 degrees at 1800 to 31 degrees at 2100 and 36 degrees at 2300, heating systems that had been operating continuously began to restore indoor temperatures. However, recovery rates varied significantly based on how far indoor temperatures had declined during the day. Homes that had maintained indoor temperatures above 68 degrees Fahrenheit throughout the event returned to 70 degrees Fahrenheit set points within 1 to 2 hours as outdoor temperatures rose. Homes that had fallen to 65 to 67 degrees Fahrenheit required 3 to 5 hours to return to set point despite rising outdoor temperatures and continuous furnace operation. Homes that had dropped below 63 degrees Fahrenheit required 6 to 9 hours for full temperature recovery. This pattern reflected thermal mass effects and the cumulative nature of heat loss. Building materials, drywall, framing, furniture, flooring, had cooled throughout the day as indoor temperatures declined. Restoring indoor air temperature to 70 degrees Fahrenheit did not immediately restore these materials to equilibrium temperature. Heat continued to flow from warm air to cooler building materials, slowing the rate at which thermostats registered temperature rise and extending the period during which heating systems operated at full output. By 0200 Thursday morning, outdoor temperatures had risen to 42 degrees Fahrenheit, and most homes had returned to set point temperatures, but heating systems had operated continuously for periods ranging from 16 hours in well-performing structures to 22 hours in poorly performing ones. Total runtime for the cold event exceeded typical weekly heating runtime in many installations, compressing normal wear cycles and maintenance intervals into a single operational period. Post-event analysis by utility companies, HVAC contractors, and building performance analysts focused on operational data rather than anecdotal reports. CenterPoint Energy documented the event as the longest sustained period of below freezing temperatures in Houston since February 2021, noting that residential gas demand exceeded planning projections based on historical temperature data. ERCOT analysis confirmed grid stability throughout the event, while noting that residential electric heating load reached levels typically associated with peak summer cooling demand, a condition not reflected in winter capacity planning models. HVAC service call logs from the Houston metro area showed a 340% increase in service requests on Wednesday and Thursday compared to typical January call volumes, with approximately 73% of calls involving complaints of insufficient heat rather than equipment malfunction. Diagnostic testing in these cases typically revealed normally functioning equipment operating within specifications but unable to maintain set point temperatures under ambient conditions. Building science consultations conducted in the weeks following the event identified thermal envelope deficiencies as the primary factor in structures experiencing the most severe temperature loss, with recommendations focusing on air sealing, insulation upgrades, and window replacements rather than heating equipment replacement. Manual J recalculation for sample homes using 26 degrees Fahrenheit outdoor design temperature instead of 32 degrees Fahrenheit recommended heating equipment 12 to 18% larger than existing installations, though implementation of such upgrades remained uncommon given the infrequency of sustained freezing conditions in the Houston climate zone. The event was documented in utility planning records, building performance databases, and HVAC industry case studies as an example of system operation at the margins of design assumptions, where infrastructure functioned as intended while environmental conditions persisted just beyond the statistical envelope used to define intended performance parameters.